So we spent a lot of time talking about substitution, the kinetics of substitution reactions. Another type of reaction you can have with alkyl halides are elimination reactions. In an elimination reaction, we're removing two groups. Now this can be two atoms or it could be a substrate, whatnot. So this is a little bit different than substitution. So in this, we're eliminating two atoms or two groups, and we typically form a pi bond. So what happens is and now notice here for elimination reactions, we're using a base instead of a nucleophile. So with substitution reactions, we prefer nucleophiles. And there are nucleophiles that are bases. But for substitution, we want nucleophile. For eliminations, we want bases. So the stronger the base, the more likely it's going to undergo an elimination reaction. And so what a base does is it attacks a hydrogen on a carbon that's adjacent to the carbon with the halide. Typically, this is referred to as the alpha carbon. So the base attacks a hydrogen on the alpha carbon, rips that hydrogen off, and then the lone pair of electrons goes between the two carbons to form a pi bond, and the halide leaves. And so what we form is a double bond. Now, whether this occurs in one step or in two steps will dictate whether it's going to be an E2 mechanism, which is similar to the SN2. It's in one step. It's concerted. It happens all at once. So it's a bimolecular one-step mechanism, or whether it's going to be E1, where it goes in two steps. And again, the first step is to form the carbocation. Then the base attacks, and you get your alkene. Now, whether or not it goes through E2 or E1 depends on the strength of the base. Strong bases will undergo E2 as long as the alkyl halide, of course, is either a methyl primary or even secondary alkyl halide. E1 typically is for tertiary alkyl halides because they can't undergo E2. So typically E1 is with your tertiary. The other ones generally are E2. And by the way, when we go over a chart in a little bit, you see most of these reactions, if you use a strong base, strong nucleophile, undergo E2 process. So again, with E1 reactions, since this is a SN1 mechanism, so we have a tertiary alkyl halide. Notice that there's three groups attached to this carbon. So first, what happens is the halide leaves, we form our carbocation. Now the base, now notice this is hydroxide, it's a base, as well as a nucleophile, but here it's behaving as a base. It attacks this hydrogen on an adjacent carbon, ripping that off, and then the lone pair of electrons go between the two carbons to form the alkene. And again, this is a two-step mechanism. The first step, we form our carbocation. The second step, the base attacks the carbocation, and we get our alkene and halide. And generally, these are endothermic, and we'll explain why in a second. Here it shows exo, but these are generally endothermic reactions. And so what's happening at the transition states? The carbon-bromine bond gets longer, and eventually when it rolls down into this minimum, it's broken, and we form our carbocation and halide. So with E1, just to kind of show you again the steps of the mechanism. So here when we use, for example, water would be a base that could undergo E1 mechanism. So what happens is the bromine leaves, we form our carbocation, Water attacks the hydrogen on the carbon adjacent to the carbocation, and then we get our alkene. And again, this is a two-step unimolecular mechanism. So with E1, typically these form with what we call weak bases. So here we have a tertiary alkyl halide. We have a hydroxide. The first step is the E1 mechanism. We form our carbocation. So the halide leaves. And then the base attacks, again, the hydrogen that is adjacent to the carbocation. Now you may say, well, hey, the double bond formed here, but with elimination reactions, you can have a variety of products. So for example, instead of this hydrogen, let's say the base attacked one of the hydrogens here. So then you would get a double bond here. So in some elimination reactions, you can have multiple products depending on where the strong base attacks the hydrogen. So that does happen sometimes with elimination reactions. Now with E2 reactions, we're looking at a concerted reaction, so everything happens at once. And with E2, which is generally what most elimination reactions are, or E2, if you're using a strong base, you're always going to have an E2 mechanism as long as it's a methyl primary or secondary alkyl halide. Now some examples of strong bases that are strong nucleophiles are things like hydroxide and alkoxides. Now alkoxides, what they are, if you imagine an alcohol and just remove the hydrogen. So alkoxides are a deprotonated, if you want to call it that, alcohol. So for example, CH3O minus is called methoxide. So these two groups are examples of things that are strong bases and strong nucleophiles. The reason I want to mention this is because we can have some bases that are just strong bases but poor nucleophiles. And the two most common examples of reactants that are strong bases and poor nucleophiles is one called lithium diisopropylamine, which is shown here. LDA is its common abbreviation. Again, this is a strong base but a weak nucleophile. And the reason it's a weak nucleophile is because it's very bulky. So this would only undergo E2 mechanism because it's a strong base and a weak nucleophile. Another example of a strong base but a weak nucleophile is potassium T-butoxide. And the way they would write this, something like this. I have it written somewhere, so we'll see in a second. But again, potassium T-butoxide and lithium diisopropylamine are what we call strong bases but poor nucleophiles. And so they would only undergo elimination reactions, because what it means is when you're a strong base, you like to rip off protons. And so since these are strong bases but poor nucleophiles, these can only undergo elimination reactions. So they can only remove protons and form double bonds. Again, those are the two most common examples of, again, strong base poor nucleophile, lithium diisopropylamine, LDA, and potassium T-butoxide shown here. These are the only two we're going to cover in this class. As long as you know these two, these are the only strong base, poor or weak nucleophile that we will discuss. So what happens, since we're using lithium diisopropylamine, it attacks as a base the hydrogen. Since this is very quick, the electrons go to the carbon-carbon bond, and then the bromine leaves. So this would be an E2 mechanism. And most elimination reactions are endogonic or endothermic reactions. And the reason that they're endothermic is because what's happening is we're forming a bond between the nitrogen and the hydrogen, and then the carbon-hydrogen bond is broken, and we're forming a bond between two carbons, and a carbon-bromine bond is being broken. So what's happening is we're going from something that has all sigma bonds, so we have 3 sigma bonds, to something that has a pi bond and a sigma bond. And so therefore, when we go from sigma bonds to a pi bond and a sigma bond, the pi bond is a higher energy orbital. Therefore, you're adding electrons into a higher energy orbital. That causes it to be less stable, therefore endothermic. So that's why elimination reactions are typically endogonic reactions or processes. So we have a secondary alkyl halide, we have an alkoxide. So this is similar to ethanol, except we removed a hydrogen from it. So the alkoxide here is called ethoxide. And these are strong bases, these alkoxides. And so what's going to happen is, since we have a strong base, we have a secondary alkyl halide. This would undergo E2 mechanism. So what would happen is the base would attack the hydrogen or the alpha hydrogen, and then once that base rips off that proton, the electrons come here, form a double bond, and the iodine leaves. So we get ethanol and our alkene shown here. And again, the way I know that this is going to be an E2 mechanism, we have a secondary alkyl halide, we have an alkoxide, which is a strong base, and the strong base is going to react so fast, it's going to rip off this proton so quickly, so it's going to be a concerted reaction. And that's why I know it's going to be an E2 mechanism. So with E2 mechanisms, remember there's no reaction intermediate, it all happens at once. So when you take a strong base, react it with an alkyl halide, what happens is the carbon halide bond starts to elongate while the base is starting to react with the hydrogen on the adjacent carbon. And so this bond starts to form, the carbon halide bond starts to break, and we start to form a pi bond between the two carbons. And that's what's occurring at the transition state. Now, after we roll down the transition state, the halide leaves, the hydrogen breaks apart, and we form a carbon-carbon double bond. So here, this again is a one-step biomolecular mechanism. So now this is an important chart here, because this kind of tells you the different types of reactions you can encounter with different types of alkyl halides and nucleophiles and bases. So for example, if we have a strong nucleophile strong base, and we have a methyl halide, it's going to undergo SN2 reaction. And the reason it can only undergo SN2 reaction is if we look at a methyl alkyl halide, it only has one carbon, it cannot form a double bond. So what's a strong nucleophile, strong base? These are things like hydroxide, alkoxides, and even deprotonated amines as well. So these are strong bases, strong nucleophile. If you have a methyl halide, it's most likely going to undergo, well, it's only going to undergo SN2. The same holds for primary alkyl halides. They tend, with a strong nucleophile and strong base, they tend to undergo SN2. Now, these are just general trends. Of course, there are exceptions that could occur. Now, with a secondary alkyl halide, with a strong nucleophile, strong base, we form E2 products. So it prefers the E2 over the SN2. Now, with tertiary, we can't have SN2, so if you use a strong base, it can undergo E2 mechanism. So I might have said earlier that you can't undergo E2, but I was incorrect. So for tertiary, if it's a strong base, strong nucleophile, it can undergo E2, but it cannot undergo SN2. Now with a strong nucleophile and a weak base, so what you have here, if you have a weak base and a strong nucleophile, it's only going to prefer the substitution reactions. Because it's a weak base, it's not going to undergo elimination reactions. So what's a strong nucleophile and a weak base? Let's see. Strong nucleophiles and weak bases are things like amines, thiols, or the deprotonated version of a thiol, cyanide, azide, iodide, acetate, or acetate-like carboxylates, actually is what it is. So these are examples of strong nucleophiles but weak bases. So these are examples of things that will only generate an SN2 product. That's going for methyl first degree secondary alkyl halides, but no tertiary. So with a strong nucleophile and a weak base, you cannot undergo a substitution reaction with a third degree alkyl halide. Now with a weak nucleophile and a strong base, again, the two that I mentioned, potassium T-butoxide and lithium diisopropylamine, these will undergo only E2 mechanisms. And so notice that it will not react with a methyl halide because methyl halides cannot form double bonds. So if you use something like lithium diisopropylamine and you try to react it with methyl bromide, no reaction will occur. It has to be at least a first, second, or tertiary alkyl halide. And then we have our weak nucleophiles, weak bases. These tend to undergo SN1, E1 mechanisms. So with the methyl and the primary, generally these are no reactions, but for secondary and tertiary, you can have a mixture of products. So you can have a substitution and elimination products when you use a weak nucleophile and a weak base. And these are things like water, alcohols, and carboxylic acids. And so it's very good to understand this chart because this will help you identify what types of products are used when you use a strong nucleophile, strong base, such as hydroxide. You only get SN2 or E2 products. But if you switch over to a strong nucleophile and a weak base, you only get SN2 products, and a tertiary cannot react with a strong nucleophile weak base. And so once you know these, then you can help you identify what products are produced. Now, as far as knowing the different types of nucleophiles and bases with their strength, I'm only going to use the ones that are on the charts posted on the slides. So if it's not listed here, you won't be seen on, say, an exam or a quiz. So only these are the ones that I will use as for questions. We're going to look at one more chart to help kind of summarize all of what we said here. And I like this chart because this is a good illustration of the different types of products you can have. So let's say we use a primary alkyl halide. So this is a 1-degree alkyl halide. And we use a strong nucleophile, strong base. And again, ethoxide, if you go back to the previous chart, is an alkoxide, which is a strong nucleophile, strong base. And notice that we use DMF, which is a polar aprotic solvent, because you see the products are the SN2 and E2 products. And so when you use a strong nucleophile and a strong base, and you use a primary alkyl halide, most of what you get is the substitution product, and you get very little of the elimination product. So we get a mixture of products. But now if we go and we change the alkyl halide to a secondary alkyl halide, and we use the same reactant ethoxide, which again is a strong nucleophile, strong base, you see that we get, again, a mixture of products. And I apologize, this is not a secondary alkyl halide. This is still a primary alkyl halide. But the difference between this primary alkyl halide and this primary alkyl halide is this one is more bulky. So since it's more bulky, it prefers the elimination more now than the substitution. So now we get a mixture of elimination and substitution products. And again, the reason we get more elimination products is, remember, SN2 does a backside attack. So when this gets more bulky, we prefer more of the elimination. So now it's easier to form a double bond. So now we get a mixture of substitution and elimination, like roughly 40-60. But now if we go to a secondary alkyl halide, and again we're using the same type of reactant ethoxide. With a secondary, you see that we get majority elimination product and very little substitution product. So again, that strong base rips off that proton very quickly, and therefore it forms more of the elimination product and less of the substitution product. Now we go to the tertiary alkyl halide, and again we're using a strong base, strong nucleophile, and since this is tertiary, the only product we can form is the E2 product. So that's 100% of the elimination product. Now if we switch from sodium ethoxide and we go to sodium azide, which is a good nucleophile but a weak base, and notice here we change the solvent to methanol, which is a polar protic solvent. Now we get the substitution reaction, which is SN1, which is the majority of what the product is. But you see we also get, since methanol is a weak nucleophile, we also get some product from the solvent. And then we get a little bit of product from the elimination reaction, because azide is a weak base. We get a little bit of the E1 product. So as you can see, in most of these combinations of alkyl halides, if you have a strong nucleophile and strong base, you're generally going to get SN2, E2 products depending on the alkyl halide. But if you have a tertiary alkyl halide and you have a weak base and a good nucleophile, then you're going to get mostly SN1 product and then a mixture of SN1 product with the solvent if you use a protic polar solvent and E1 product.